The development and operation of reusable spacecraft like the Space Shuttle and the Soviet Buran marked a significant milestone in the history of manned space exploration. These spacecraft required extensive design and research efforts to address the unique challenges posed by high-altitude and high-speed flight. This journey toward reusable spacecraft began decades earlier, with pioneering research and testing of rocket technology. By 1954, NASA recognized the need for a new type of rocket aircraft capable of exploring altitudes between 50 and 100 kilometers, and achieving speeds up to 7,200 kilometers per h. This led to the development of the X-15, an experimental rocket plane designed to fulfill these ambitious requirements. The X-15 was equipped with a powerful rocket engine producing about 27 tons of thrust. The X-15 program aimed to gather crucial data for future aerospace projects, including the Dinosaur suborbital combat vehicle. The X-15's missions provided valuable insights into dynamic heating, structural heat resistance, the characteristics of throttleable rocket engines, and the conditions necessary for sustained aerolife at high altitudes. Additionally, the program contributed to geophysical research and improved understanding of cosmic radiation in the upper atmosphere. Manufactured by North American Aviation Inc., 3 rocket-powered X-15 aircraft flew a total of 199 times as part of a joint research program involving NASA, the U.S. Air Force, and the Navy. The first unpowered glide flight was conducted by North American pilot Scott Crossfield on June 8, 1959. The program concluded with NASA pilot William H. Dana's final flight on October 24, 1968. All flights took place within the high range, primarily east of Edwards Air Force Base in California and NASA's Flight Research Center. The program involved 12 pilots in total, 5 from NASA, 5 from the Air Force, 1 from the Navy, and Scott Crossfield from North American. Pilots generally followed one of 2 flight profiles: a speed profile, where the pilot maintained a level altitude until descent, and a high-altitude profile, where the pilot maintained a steep climb until reaching altitude before descending. Due to the rocket engine's significant fuel consumption, the X-15 was air-launched from a B-52 aircraft at approximately 45,000 feet and speeds of around 500 miles per hour. The rocket engine provided thrust for the first 80 to 120 seconds of flight, depending on the mission. The remainder of the 8 to 12-minute flight was unpowered, culminating in a 200-minute glide landing. The X-15's landing gear included a nose wheel without steering and main gear with skids, necessitating landings on dry lake beds. The X-15 was a groundbreaking research aircraft that succeeded the early X-planes, which explored flight speeds from just below Mach 1 to Mach 3.2. By 1952, the National Advisory Committee for Aeronautics, NACA, had started investigating spaceflight and its associated challenges. In 1954, NACA's Research Airplane Projects panel emphasized the need for a new aircraft to study hypersonic and spaceflight. NACA outlined the requirements for what would become the X-15 and presented them to the Air Force and Navy in July of that year. A collaborative project was formalized in December 1954, and by September 1955, North American Aviation was selected to develop 3 X-15 aircraft. Chief Project Engineer Charles Feltz led the North American team, with technical input from NACA's Langley Aeronautical Laboratory, now NASA's Langley Research Center, in Virginia, and the High Speed Flight Station, later known as Dryden, in California. The X-15 was designed as a single-seat mid-wing monoplane to investigate high aerodynamic heating rates, stability and control, physiological effects, and other hypersonic flight challenges above Mach 5. Initially, due to the unavailability of the throttleable XLR-99 engine from Reaction Motors Division of Thiokol Chemical Corps, the X-15 flew with 2 XLR-11 engines generating 16,380 pounds of thrust. Once the XLR-99 was installed, thrust increased dramatically to 57,000 pounds. For conventional flight within the dense atmosphere, The X-15 employed standard aerodynamic controls, rudder surfaces on the vertical stabilizers for yaw, left-right nose movement, and canted horizontal tail surfaces for pitch, nose up-down movement, and roll, wing tilt. Outside the Earth's atmosphere, the X-15 utilized a reaction control system with hydrogen peroxide thrust rockets, nose rockets for pitch and yaw, and wing rockets for roll control. The X-15's outer skin was made of a nickel-chrome alloy called Inconel X, designed to handle the extreme aerodynamic heating during atmospheric flight. The aircraft's cabin, constructed from aluminum, was thermally isolated from the outer structure to maintain a cool environment for the pilot. The first X-15 arrived at NASA's high-speed flight station in early 1959, marking the beginning of a remarkable era in aviation history. Scott Crossfield, who had contributed to the design of the X-15, initiated the contractor demonstration flights. Throughout its research program, the X-15 set unofficial world speed and altitude records reaching 4,520 miles per hour, Mach 6.7, on October 3, 1967, with Air Force pilot Pete Knight at the controls, and an altitude of 354,200 feet on August 22, 1963, with NASA pilot Joseph Walker. Beyond these impressive records, the X-15 delved deep into the realms of hypersonic aerodynamic performance and heating rates, structural behavior under extreme conditions, stability and control during atmospheric exit and re-entry, and pilot performance and physiology. This comprehensive research generated data for over 765 reports, contributing immensely to aerospace knowledge. As noted by Dryden chief scientist Ken Iliff and aerospace research engineer Mary Schaefer, the X-15 provided critical hypersonic data on aircraft performance, stability, control, materials, shock interaction, the hypersonic turbulent boundary layer, skin friction, reaction-controlled jets, aerodynamic heating, and heat transfer. Understanding and controlling the boundary layer, the thin layer of air adjacent to the aircraft's surface, was essential for enhancing aircraft performance. John Becker, a distinguished researcher from Langley and an early advocate of the X-15 program, identified 25 specific accomplishments from this effort. The X-15 not only set speed and altitude benchmarks, but also significantly advanced our understanding of flight dynamics in extreme conditions, laying the groundwork for future aerospace innovations and space exploration programs. The X-15, with the exception of the modified X-15A2, measured roughly 50 feet in length and had a 22-foot wingspan. Its distinctive wedge-shaped vertical tail stood 13 feet high. Due to the lower vertical tail extending below the landing skids when deployed, a portion of it was designed to be jettisoned just before landing, safely parachuting to the ground for recovery. The aircraft was powered by a Thiokol, Reaction Motors Division, XLR-99 throttleable rocket engine using anhydrous ammonia and liquid oxygen, providing a maximum thrust of 57,000 pounds and a minimum thrust of 28,000 pounds. At launch, the aircraft weighed 31,275 pounds, decreasing to 12,295 pounds by burnout. The X-15A2, an extensively modified version of the second X-15 aircraft, was delivered to NASA in February 1964. Among its new features was a 28-inch fuselage extension designed to carry liquid hydrogen for a supersonic combustion ramjet. Although this ramjet was flown as a dummy, it was never actually tested. Additionally, the X-15A2 had external tanks for liquid ammonia and liquid oxygen, which provided approximately 60 seconds of extra engine burn. These modifications enabled the X-15A2 to achieve Mach 6.7, but also increased its weight to nearly 57,000 pounds and significantly added to the drag experienced during flight. The X-15 program, while highly successful, was not without its challenges, including emergency landings and accidents. Only 2 incidents resulted in serious injuries or fatalities. On November 9, 1962, pilot Jack McKay experienced an engine failure and was forced to land at Mud Lake, Nevada. Upon landing, the landing gear collapsed, causing the aircraft to flip onto its back. McKay sustained injuries from the incident but managed to recover sufficiently to resume flying. However, the long-term effects of his injuries eventually led to his retirement. The second, more tragic incident occurred on November 15, 1967, during Michael Adams's seventh flight. Adams encountered a technical problem with the adaptive flight control system, which caused the aircraft to enter a spin. Although he managed to recover from the spin, he was unable to correct an inverted dive. The X-15 No. 3 crashed, resulting in Adams's death.